So let's look at our n-particle wave function. Well, we have already seen that this can be written as a sum of single particle wave functions.
These systems are either used wasn't for your primary part, and we have some kind of system which is like a conventional.
Well, if you have a mixture of systems, you can basically divide your system into subsystems. Each subsystem has one kind of identical particle. So if you know how to deal with pure systems, in the sense that systems that have just a single kind of particle, well, then you know how to deal with the mixture. Then when you bring them together, if you have different kinds of particles, they will exchange energy with each other. So they will all have the same temperature. They will not exchange particles. But I mean, you can still play with them. You can write down the total, the free energy of the whole system by just summing their free energies at the same temperature and study all their properties. Now, of course, I have to I have to make sure that this is completely symmetric or completely anti-symmetric. These K1, K2, Kn's, they are what I use to denote the quantum numbers of single particle states. R1, R2, Rn, they are the positions of my particles. Of course, I have to consider all possible exchanges between the positions of particles. So to consider all possible exchanges, you can sum over all permutations. And let me just multiply this, what I call minus 1 to the p. This is the sign signature of the permutation p. Now, what does a permutation do? If we just get some numbers between 1 and n, it maps. There are different ways of showing the permutations. For example, you can have a permutation which maps 1 to 5, 2 to 3, n to 1, and all between. It just shuffles all these integers. This is one way of showing a permutation. Or you can say that you can also use this notation. What this means is, if this is my permutation, P of I is J, P of J is I. Or let's say a concrete example, 1, 2, 4, 3. If you have such a permutation, this permutation takes 1. Well, this is 1. The next one is 2. So P1 is 2. P2 is 4. P3, these are cyclic. So P3, go to the front, is just 1. And P4, well, this is 4, the next one is 3. And let's say P5 with this permutation is just 5, it doesn't change, 5. This is just notations, ways of showing the permutations. Let me consider a simpler permutation, let's say 1, 2, 3. It will take P1 to 2, it will take 2 to 3, and 3 to 1. Well, I can also write the same permutation as the product of two permutations. Well, what does this do? Well, the first one just takes 1 to 2. The second one, well, doesn't do anything with 2. So 2 stays as 2. 2, if you apply the first permutation, it becomes 1. And then the second permutation takes 1 to 3. So 2 became 3. If you start with 3, the first permutation doesn't do anything to 3. The second permutation replaces 3 by 1. So you see that this permutation, which I defined here, is actually the same as this permutation, which is here. It just permutes in 2 steps. I can write the same thing as 1, 3, 5, 4, 4, 5, 1, 2. What this way of writing will do, it will take 1 to 2. This second permutation will not do anything to 2. This one will not do anything to 2. And this one will not do anything to 2. If you start with 2, this one will convert 2 to 1. This one will not do anything to 1. The next one also will not do anything to 1. The last one will permute 1 to 3. If you start with 3, the first 3 will not do anything to 3. The last one will convert 3 to 1. If you start with 4, it seems as if it does something to 4. Well, the first one will not do anything with 4. The second one will convert 4 to 5. The third one will convert 5 back to 4. And the last one will be 4. So 4 will remain as 4. And similarly for 5. If you start with 5, the first one will not do anything. The second one will permute 5 to 4. The third one will permute 4 to 5. And the last one will not do anything to 5. So all these 3 ways of writing the permutations, they give me the same permutation. So one thing you should note is here I wrote a given permutation in terms of the product of 2 permutations that just permute 2 numbers. Here I wrote the same thing, the same permutation, as the product of 4 permutations that just each one of which just permit the 2 numbers. So this decomposition of a given permutation in terms of products of simpler permutations of just 2 numbers is not unique. You can write it in infinitely many ways. But there will be one thing that will not change. If a given permutation is written in terms of an even number of permutations of 2 numbers, in whichever way you write, there are infinitely many ways of writing it, they will all contain even number of permutations. So there is no way you can write this permutation as a product of 5 permutations of 2 numbers. It will always be even. Well, if you have an even number, it's either even or odd. So in whichever way you write -1 to the number of pair permutations, will be independent of how you write your permutation. This by pair permutation, I just mean permutations that just permit 2 numbers, like these ones. This is called the signature of the permutation. You see, given a permutation, there will be infinitely many ways of writing it, but the signature of the permutation will be independent of how you write it. it will be minus 1 to the number of pair permutations you have. So this permutation 1, 2, 3 is an even permutation. 1, 2, this is an odd permutation. So this number over here is just the signature of the permutation. Of course, well, let me write it in this way. Let me put eta p here, where eta is equal to minus 1 for fermions plus 1 for bosons. Basically, I have the signature of the permutation appearing over there for fermions, and just 1 will appear for bosons. This will make sure that my wave function is completely symmetric or completely antisymmetric. This is mainly a notation. Now, of course, it might happen that some of these states, K1, K2, Kn, they might be identical. I mean, I can have, I don't know, 2 bosons in a given single particle state. So if I would like to make that also explicit, I can write the wave functions in this one, these product wave functions. Instead of writing them like this explicitly, I can also write them as, let's say, n alpha, where n alpha is the number of particles in the state alpha. Let's say that alpha can be 1, 2, 3 arbitrarily. So this Ri will be J is equal to 1 to N1 U1 Rj. So there are N1 particles in the state 1. J is equal to 1 to N2 U2 or N1 plus J. Different particles are in the states U2. I have all these products. Then, of course, once you have these products, you have to sum overall permutations. Let me put Pj and P N1 plus J over there. Sum with eta to the P. This is my wave function. So what is the normalization? You see, for example, okay, this is the general, for a general number of particles. For simplicity, let me just consider 2 particles. Two states, and let's say 2 fermions. Then the wave function will be psi1 R1, psi2 R2. The permutation of R1 and R2 will be psi1 R2, psi2 R1. What is the normalization of this wave function? If psi1 and psi2 are normalized to 1, one over square root of 2. Let's say 2 factorial. Yeah, if you have, let's say, n of them, n particles, n fermions in n different states, then I would get psi is equal to 1 over n factorial square root This is my wave function. Remember, eventually I will be calculating the density matrix for these states. And when I'm calculating the density matrix, I will have psi star some operator psi, which will be 1 over n factorial. Well, almost it's as if I have the Gibbs correction in the density matrix now because of this normalization. Well, unfortunately, things are not so simple. Let's look at, as a second example, two states and two bosons in the state 1. In two bosons, one in state 1, one in state 2. Well, what will change is just the sign. This is what will change. Well, again, I have 2 factorial. Let's look at a different case. 2 states, 2 bosons, both in state 1. My state is psi 1 R1, psi 1 R2. Basically, that's it. There are no 1 over n factorials or 1 over 2 factorial. It practically is not there. But exchanging R1 and R2 doesn't give me a new state. It stays the same. The wave function is symmetric. So normalization gets a bit problematic. Well, if I would like to write it similar to this one, what I would get is psi 1 R1, psi 1 R2 plus psi 1 R2, psi 1 R1. But now the correction factor is 1 over 2. Basically, what's happening here is I have these products. If I consider, here I am considering all possible permutations. But permuting R1 and R2 just gives me the same state. So the coefficients add now. That is what is making a difference. So the question then is, given these numbers and alpha, how many permutations are there that would not give me a different product here? I'm summing over all permutations of that product wave function. But not all permutations gives me a different product wave function. Some of the permutations will give me exactly the same product wave function, like in this one. You see, I have this product wave function. If I consider the permutation, this is another product wave function, but these two product wave functions are identical. So if you look at over here, any permutation that will permute this n1 coordinates will give me the same wave function. Any permutation that will permute these n2 coordinates will give me the same wave function. So basically, I will have n1 factorial. There are n1 factorial permutations of the first n1 coordinates, n2 factorial permutations of the second n2 coordinates, etc. So these many permutations don't give me a new state, don't give me a new product wave function. It's just like here, I am just summing them up. So in the normalization, I have to take that into account. Now let's do another example of 3 states. No, 2 states still. 3 bosons. 2 in state 1 and 1 in state 2. Well, all the possible permutations of 3 numbers are 1, 2, 1, 3, 2, 3, 1, 2, 3, 3, 2, 1, and identity. These are all the 6 permutations of 3 coordinates. Now, what will the symmetric wave function will be? Let's say psi 1 R1, psi 1 R2, psi 2 R3. This is one term. Now, this tells me that I should just permute 1 and 2. Psi 1 R2, psi 2 R1, psi 1 R1, psi 2 R3. This tells me that I should permute 1 and 3. So it's psi 1 R3, psi 1 R2, psi 2 R1. This tells me I should permute 2 and 3. Psi 1 R1, psi 1 R3, psi 1, psi 2 R2. Then I have this permutation, 1 is replaced by 2, 2 is replaced by 3. Psi 1 R2, psi 1 R3, psi 2 R1. And finally, psi 1 R3, psi 1 R1, psi 2 R2. Okay, these are all the terms. Let's look at the normalization. You see, not all these 6 terms are distinct. The first 2 lines are the same. And the next 2 lines are the same. No. Okay, this line, these 2 lines are the same. These 2 lines are the same. And these 2 lines are the same. They are all added. So basically, I end up having, let me add the normalization, whatever normalization will be. I will have 2 psi 1 R1, psi 1 R2, psi 2 R3, plus 2 psi 1 R3, psi 1 R2, psi 2 R1, plus 2 psi 1 R3, psi 1 R1, psi 2 R2.
Excuse me, I don't understand. For example, why did you say that those 2 lines are the same? in which way they are components?
Well, I mean, psi1 are, in the second line, just exchange psi1 r2 and psi1 r1. They're just products. I mean, you can just ordinary multiplication, change their places, you obtain
They
the.
commute, there is no.
These are just functions. I'm talking about wave functions, no operators here. There's the normalization. Well, you see, 2's, they get out. Now, what is n squared should be, or 2 squared times 1 plus 1 plus 1 times n squared should be 1. This is the proper normalization. Now, what is this 2? Well, that is the number of ways I exchange the coordinates, which doesn't give me a new product wave function. So if I just exchange R1 and R2, I get the same product wave function. Similarly, in these two terms, if I exchange R2 and R3, I get the same product wave function. How many ways can we do that? Well, we just wrote it, n alpha factorial. In this particular case, n1 is 2, n2 is 1, and all the other states are 0. So this is just 2 in this particular case. Now then the question is, how many such combinations are there? Those are the permutations that don't give me the same product wave function. In general, I have n factorial permutations of my numbers, n numbers. This many of them give me the same product wave function. So this is the number of permutations that give me the same, that do not give me. That doesn't give me the same product wave function. So these are those terms. In this particular case, n was 3, and product of n alpha factorials is 2. So there's 3 factorial divided by 2, there are 3. Now these are those 3 terms. So in general, what I would get, product of n alpha factorial, this is this overall factor. That thing squared plus times the number of such terms. Now the number of such terms is n factorial divided by the product of n alpha factorial times my normalization, so this is squared. My normalization factor squared should be equal to 1. So you can determine what the normalization factor is, and in particular, the normalization factor is not just 1 over n factorial. Now, the exact form of this normalization, we won't really care about that, but the important thing is it's not 1 over square root of n factorial. or its square is not 1 over n factorial, which was the Gibbs correction. So Gibbs correction doesn't actually work exactly. It's approximately true if the n alphas are 0 or 1, or n alphas, we will see that the average of n alphas is much less than 1. The Gibbs correction factor works. We recover the Maxwell-Boltzmann limit, but in general it will not be correct. Now, another thing that you should pay attention to is, let's go back. You see, given n alpha is the number of particles in a given single particle state, the wave function is unique. There's a single wave function I can write for my fermions or bosons. So when I'm counting my microstates, it's enough to count these n alphas. And that will be enough. And for each set n alpha corresponds one microstate. Now, the easiest treatment will be in the grand canonical ensemble. Let's look at the grand canonical. In the grand canonical ensemble, non-interacting particles. This is what I would like to look at. We need to calculate the grand canonical partition function. Sum over all microstates of e to power minus beta e minus mu n. Well, the energy of my system, the total number of particles in my system will be sum over all single particle states of the number of particles in that single particle state. The energy, well, if I have n alpha particles in a single particle state with energy epsilon alpha, this will be the energy of all the particles in the state alpha. Well, then if I sum over all particles, this is the total energy of my system. Now, grand canonical partition function then becomes, well, sum over the microstates. Each microstate is determined uniquely by these numbers n alpha of exponent minus beta sum over alpha of n alpha times epsilon alpha minus mu. The mu term, mu I can take out of that alpha summation. That will give me the total number of particles. So that will just give me minus mu. And the epsilon alpha term gives me the total energy. Well, let's see. This is sum over n1 from 0 to infinity, sum over n2 from 0 to infinity. Well, I have infinitely many single particle states. Practically, I have infinitely many sums over there. The exponent of a sum I can write as the product of the exponents. Which I can write as product over alpha of sum over n alpha from 0 to infinity. No, sorry. Sum over n alpha. It will start from 0, but we will see it. I mean, for fermions, it's at most 1. For bosons, it can be infinity. sorry, here I have an n alpha also. This is Q. Well, what is that sum? Okay, for fermions, n alpha, the number of states in a given state can be 0 or 1, so that sum will be just 1 plus e to power minus beta epsilon alpha minus mu. For bosons, it will be, well, n alpha goes from 0 up to infinity. So if I sum them up, it will be 1 minus e to power minus beta epsilon alpha minus mu to the power minus 1 over that one number. Well, let me write it slightly differently. That will be 1 minus a e to power minus beta epsilon alpha minus mu to the power 1 over a, plus a plus 1 over a where a is equal to 1 for fermions and minus 1 for bosons. Well, let me just change the sign. Fermions always have this minus signs appearing here and there. So now I can write my grand canonical partition function. Again, A is minus 1 for fermions plus 1 for bosons. Oh, sorry. The grand partition function will be this product over all single particle states. Remember, we were talking about the Q potential when we were discussing the grand canonical partition function, which was PV over KT. This is just the logarithm of Q. Now, logarithm of Q just becomes minus 1 over A. Now, the product, logarithm of the product just becomes the sum of the logarithms. This is the Q potential. Let me emphasize that this is sum over single particle states. It's not the sum over all the microstates of my large system. It is sum over the single particle states that each one of my particles can be. Those are the states that appear in these product wave functions. Psi 1 is one single particle state, psi 2 is a different single particle state. So any questions up to here? Now, let us also look at what would happen if we would like to calculate the number of particles in this system. Well, the number of particles in my system, the total number of the particles in my system, in terms of the Q potential, remember this was Z times derivative with respect to Z of the Q potential, where Z was e to power beta mu. This is how we can calculate the number of particles in my system. Of course, when I'm taking this derivative with respect to Z, I'm keeping beta constant, beta and V. So let me take this derivative. This is z times derivative with respect to z of minus 1 over a sum over of logarithm of 1 minus a z e to power minus beta epsilon alpha which will be equal to z times minus 1 over a sum over alpha. Well, if we take the derivative of that logarithm with respect to z, we would get minus a e to power minus beta epsilon alpha divided by 1 minus a z e to power minus beta epsilon alpha. This minus a cancel this minus 1 over a. In fact, that was one of the reasons why I wrote the exponent as 1 over a. This is equal to z times e to power minus beta epsilon alpha divided by 1 minus a z e to power minus beta epsilon alpha. Sum over alpha. Okay, just one more step. 1 over e to power beta epsilon alpha z inverse minus a. Well, each one of those terms appearing there is the number of particles in the state in the state alpha. This is equal to 1 over e to power beta minus mu minus a. Now for fermions, a is, remember, minus 1. The average number of particles in a given state is 1 over e to power beta epsilon alpha minus mu plus 1. This is what we call the Fermi-Dirac distribution. For bosons, now note that this is less than 1. Exponent is positive. If you add 1 to it, you get a number larger than 1. So 1 over a number larger than 1, you get a number less than 1. For bosons, if you calculate the average number of particles, you will get 1 over e to power beta epsilon alpha minus mu minus 1, which is called the Bose-Einstein statistics. Well, it can be less than 1, larger than 1. We will study it in more detail. What about for Maxwell-Boltzmann? Do you remember? For Maxwell-Boltzmann particles, that's the distribution obeying the Maxwell-Boltzmann statistics. The average numbers, if you just go back and look in your notes, this is given by e to power minus beta epsilon alpha minus mu. So basically, I will generalize my definition of A. You see, this is, if you look at this expression, you recover Maxwell-Boltzmann statistics for A is equal to 0. So whatever we will do, we can use this general expression, but A is equal to minus 1 for fermions, plus 1 for bosons, and 0 for particles satisfying the Maxwell-Boltzmann statistics. Well, then you can complain. Let's go back. What about the Q potential? I have a 1 over A there. Well, if you calculate the limit as a goes to 0, the a's basically cancel. Remember, when you put a is equal to 0, the logarithm diverges. Logarithm becomes 0. 1 over a becomes 1 over 0, so it's 0 over 0. It has a finite limit. So if you take the limit, this is just sum over all alpha of e to power minus beta of this exponent for the Maxwell-Boltzmann. And that was what we had before. Okay, let's give a break now.